Very good afternoon to you, student. Today, let me again discuss one more problem on equilibrium of coplanar forces. So I'm going to solve here, though I have sent the notes. Now, what I'm going to do here, I'll just show you how we got the result of this. How I solved this question is that what the question is, a beam of weight, W, is divided by its center of gravity, C, into two portions, AC and BC. So which means that you have a beam AB. AB is a beam where the center of gravity is at point C, and that center of gravity divides the beam AB into two portions, that is A and B respectively. The beam rests in a vertical plane. One end of the beam is resting on a vertical plane on a smooth floor, and the other end against a smooth. The beam rests in a horizontal plane. Okay, in a horizontal plane. Let me check the question. Okay, in a vertical plane on a smooth floor AD and against a smooth vertical wall DB. Now a string is attached to hook at D and to the beam at a point P. If T be the tension of the string and theta phi are the angle of inclination of the beam and the string respectively to the horizontal, then show that T is equal to WA into cos theta by A plus B into sine of theta minus phi. So here let me show you the diagram. So you have here, this is the red one here is the smooth horizontal floor. Smooth horizontal floor. And this one is smooth vertical wall. And AB here is the beam. This one is a string. Okay. So you have here this AB, as you can see in the diagram, is a beam, where C here is the center of gravity. C is the center of gravity of this beam AB, which cuts it into, which divides it into two portions, that is AC is to BC of length A and B respectively. Now, as you can see in the question, a string is hooked at this point D. Okay, BD is a smooth vertical wall and AD is a smooth horizontal floor. So a string is hooked at this point D to a point P on the beam. This is the point P on the beam, where T here is the tension of the string and the phi is the angle made by this string to the horizontal, and theta is the angle of inclination made by the beam AB to the horizontal floor. Now R here is the normal reaction of the floor perpendicular, a normal reaction of the floor acting at A, and S is the normal reaction acting at B, okay, perpendicular to the smooth vertical wall. T is the tension of the string is acting in this direction because this is hooked from here to here, okay, and L here, LA is the distance, perpendicular distance of this string, DL to the point A, okay. So here what we have is, as you can see here, MC here is the CG of this beam, and since it is a center of gravity, so it is the point through which the resultant weight W of the beam acts. So here you have, this is the weight W acting vertically downwards. And the result part of this string, okay, as you can see here, it is of inclination phi to the horizontal. So the result part of this along the x-axis, along the y-axis is T sine phi, and along the x-axis it is T cos phi. So here let us solve this problem to show that the tension T of the string, this T, is equal to WA into cos theta divided by WA into cos theta divided by A plus B into sine of theta minus phi. Okay, solution. The forces acting here are the weight W, the weight W acting at C, is vertically downward. And then the number one, the forces acting here are number one, number two, the normal reaction of the horizontal floor acting at A, okay, as you can see in the diagram, and number three, the normal reaction perpendicular, the normal reaction of the vertical floor vertical wall acting at B. Number 4 is the tension T of the string. So here the string LD is attached hook at D, and it is, and at a point P, one end of it is hooked at D and the other end is, it meets the point P, it is attached to the beam at a point P. Okay, so AL here is the perpendicular distance of the string. So now let us resolve the forces horizontally, as you can see in the forces in the given diagram. Resolving the forces horizontally and vertically, we get, what are the horizontal force acting here? Because the result part of this string T, okay, whose inclination is phi, along the x-axis it is T cos phi, and along the y-axis it is T sin phi. So here the forces here, as you can see here, what is S? S here is equal to T cos phi. So the horizontal force, these are the horizontal force, this one and S. So we have S here is equal to T cos phi. Okay, T cos phi. And what are the vertical force? The vertical force here are the VW, and then tension T, sorry, here it should be this one, okay, in this direction. Sorry, let me draw it here. This T sin phi is acting downward, okay. So here R is acting upward. So here you have R is, what are the vertical force? T sin phi, R, and the weight W. So this gives you R here is equal to, the normal reaction R is equal to, because these are the opposite direction, they are the same direction, you have W plus T into sin phi. So you name it as equation 1 and this as equation 2. So what we have to do here, next we have taking moments of the forces, taking moments of the forces about A, we get. So by taking the moment of the force, what is meant by the moment of force? It is the product of the force into its perpendicular distance from that point of action. So above this point, so what are the forces here? The forces here are R, T, W, okay, R, S, T, and W. But this, since this force R is passing through this point A, so the moment of this force R above this point A will be 0. Why? Because R into its perpendicular distance will be 0. So we have here S into the moment of this force S into its perpendicular distance. So if you extend this, so the perpendicular distance of this force S from here, it is equal to BD only. So S into BD is equal to W into, what is this W? The perpendicular distance of this from W the perpendicular distance of this force W from this point A is A and W into A M, and then plus T, the tension T of the string, T into what is the perpendicular distance of this string PD or DL from the point A is equal to AL. So T into AL. Name it as equation 3. Now from the diagram, from triangle ALD, we want to find what is AL. Okay, so we have, so the angle here, you consider this triangle ALD. It is theta here, so AD here will be the hypotenuse, this DL will be the adjacent side, and AL here will be the perpendicular or the opposite side. So we have AL by AD will be equal to sine phi, which implies that AL here will be equal to AD into sine phi. Now, in triangle AMC, okay, AMC, what do we have? We want to find AM. So AM here, this is AM and this is theta, which is right angle at M. So we have AM by AC. AM by AC is equal to cos theta. Cos theta. This is right angle, okay, at M. So here this implies that AM here is equal to AC into cos theta. And what about BD in triangle, in right angle triangle, in triangle ADB? What is BD? BD here, this is theta here, so BD here is the opposite side, so you have BD by AB will be equal to sine theta, which implies that BD here will be equal to AB into sine theta. Now using this, you substitute what is AL here by this AD sine phi, and AM you replace it by AC cos phi, and BD here replaced by AB cos theta. Therefore equation 3 now becomes, therefore 3 implies, what is 3? S into what is BD? BD here we have got, it is AB into sine theta is equal to W. What is AM? AM is AC into cos theta plus what is T into AL? AL, as you can see here, it is AD sine phi. Now what is S from equation 1? S from equation 1, it is T cos phi. So you replace it by this one, T cos phi, this S, and T here also we can, okay, T will remain as it is, but AD I'm going to find what is AD, okay, in terms of AB. So, or you can write here, instead of this S, you replace it by this T cos phi. So, or T cos phi into AB sine theta is equal to W into W into AC cos theta plus T here, T into AD sine phi. The rough part here. So, or this is, you can write here, since S is equal to T cos phi from equation 1. Now our T here into cos phi, but what is AB, the length of the rod? It is A plus B, because C divides this beam AB into two portions, that is A and B. So therefore you have A plus B is the length of the rod. Here you can mention, since AB is equal to A plus, that is AC plus CB, which is equal to A plus B. So into sine theta is equal to W into AC. What is AC? AC, as you can see from the figure, it is C. So it is A into cos theta plus T into. Now what is AD? AD, if you consider this is the base. So here in triangle ADB, okay, you can see in this figure what is triangle ADB. ADB here, what is AD? AD will be the base. So AD by AB will give you sine theta. So we have AD here will be equal by AB sine theta, which implies that AD will be equal to AB sine theta. Now AB sine theta, what is the length of the beam? It is A plus B. So this implies that AD here is equal to A plus B into sine theta. So here instead of AD, you replace it by this value, that is A plus B into sine theta sine phi. Now what we have to show is to find the tension T of the string. So bring this to this side. What we have is, or you can write here, T into cos phi sine theta into A plus B. You bring this term T minus T into sine theta into sine phi into A plus B is equal to WA into cos theta. Or you can write here, since T and A plus B are common, so we can take T into sine. Sorry, here I think it should be cos, no, somewhere. See what is AM, AM, AM. AM here is AC cos theta. S into AB sin theta we have is equal to WAC into sine into AC cos theta plus T into AD sin phi. That's okay. Now what is AM? Okay. Let me go back to equation 1. T cos phi. So I have written here this as T cos phi. And what is AD? AD, okay, it is AD here. It is cos theta actually. It is cos theta. Okay, I'm right here. You consider, because this is the base as you can see in the figure. So AD by AB is equal to cos theta. So this implies that AD here is equal to AB cos theta. Cancel the above equation. So but AB here, or you can write AD here is equal to A plus B into cos theta. So now it's okay. So instead of AD, I will write it, I will replace this by cos theta. Okay, this is cos theta here, and here also you'll have, when you bring it to the left hand side, you have cos theta. So as you can see, A plus B and T are common, so you have sin theta into cos phi minus cos theta into sin phi, and then take this A plus B outside. A plus B is equal to WA into cos theta, which implies that T into, what is this sin theta? Cos phi minus cos theta sin phi. It is nothing but sine of theta minus phi into A plus B is equal to WA into cos theta. this implies that T here, the tension of the string, is equal to WA into cos theta divided by A plus B into sine of theta minus phi. So this complete the proof. We have got the tension T of the string is equal to WA cos theta by A plus B into sine theta. Let me go back, summarize this. What is the question is that a beam AB here, which is with one end resting against a smooth vertical wall BD and the other end rests against a smooth horizontal floor. Now the beam is of inclination theta to the horizontal, and next is that a string of tension, a string whose tension is T here, tension of the string is denoted by T, is hooked at this point D on there, at this point D, and then the other end is to a point P on the beam. And since C here is the center of gravity of the beam, so this C here, according to question, divides AB, the beam AB, in the two portions. AC is to BD, that is A is to B, of two lengths, A is to B. So therefore, the length of the beam AB will be equal to A plus small b. Now the weight W, since C is the center of gravity, the weight of the beam will act vertically downwards through this point C. Tension T of the string will act along this direction, and S here is the normal reaction of the smooth vertical wall perpendicular to the acting at B. R is the normal reaction of the smooth horizontal floor acting at point A. Resolved part of this phi is the inclination of the string to the horizontal. So therefore here, by resolving the forces along and perpendicular to along the x-axis and along the y-axis, we have T cos phi is this and T sin phi is this, which is in this direction. So therefore, resolving the forces horizontally and vertically, we get S here will be equal to T cos phi. They are the horizontal force, and what are the vertical force? R, W, and T sin phi. But R here is acting upward, so R here will be equal to W plus T sin phi, since T sin phi, they are in this, W and T sin phi, they are in the same direction. Next, we take the moment of the forces about this point O. So since this force R is passing through this point O at point A, so the moment of this force R about this point A will be 0. And what about the moment of the other forces? That is the other forces, that is T, W, and S. It will be equal to this S into its perpendicular distance from this point A, that is BD, is equal to W into its perpendicular distance from this point A, that is AM, is plus T into its perpendicular distance from this point A, that is AL. Now we consider the three triangles ALD. In triangle ALD, what is that? Is ALD. AL here will be the perpendicular. So you have AL by AD will give you sine theta. So you have sine phi, I mean, because we consider this triangle ALD. So you have AL is called AD sine phi, and in triangle AMC, AM here, AM by AC will give you cos theta, which implies AM is called AC cos theta, and in triangle ADB, BD by AB, it will give you sine theta. From here you'll get BD is called AB sine theta. Substitute it in equation 3. Equation 3 now becomes this one. But what is AB? S from equation 1, it is S is equal to T cos phi. So we have here T cos phi into AB sin theta. You replace S by T cos phi, and from the left hand side it will be this. Whereas next we have to find what is AD in terms of that particular length. So by considering a right angle triangle ADB, what is AD? This will be the base of inclination theta, the inclination of the beam to the horizontal. So AD will be the base. So we have AD by AB will be equal to cos theta. So we have AD by AB is called cos theta, which implies that AD is equal to AB cos theta, but AB is the length of the rod, is equal to A plus B. So substitute it here. So what we have is this, bring this T into this term to the left hand side, become minus. So you can take common T and A plus B outside. The rest here will be inside the bracket, that is sin theta into cos phi minus cos theta into sin phi. So this into A plus B is equal to WA into cos theta, which implies that T here will be equal to. So this implies that T into sin theta minus phi into A plus B is equal to WA cos theta, or T here is equal to WA cos theta divided by A plus B into sin theta minus phi. Now I hope it is clear regarding this problem, how we got the tension T of the string which is being hooked from the point D in from a point D to a point P on the beam.